Hello friends, welcome to engineering tutorial. Now in my previous video I discussed about the collector to base feedback resistor method of BJT biasing. So in today's video I'll be discussing about the voltage divider bias method. Okay, the last of the four methods which are used for DC biasing. Now it is the most widely used method to provide biasing and stabilization to circuits, transistor circuits, be it bipolar junction transistor or field effect transistor. This is a popular method which is used, the voltage divider bias method. So this is the circuit diagram of the voltage divider biasing circuit. From these two resistors you can just make out why this circuit is called as voltage divider biasing circuit. It forms the voltage divider circuit, the resistors R1 and R2, which is connected to the supply voltage VCC, to the positive end. RC is the collector resistance. One end is connected to the collector terminal and the other end is connected to VCC. Then we have the emitter resistance RE, whose one end is connected to the emitter terminal and the other end is connected to ground. Here there is a ground connection which I have not mentioned, but there is a ground connection at the bottom. Okay. Now I1 is the current which flows through R1. I2 is the current which flows through R2. IB is the base current. Now, the magnitude of the base current is of the order of microamperes, which is very small as compared to the currents which are flowing through the resistors R1 and R2. Okay, the magnitude of IB is very less as compared to I1 and I2. So here I1 is actually, when you write the KCL equation, the Kirchhoff's current law equation, I1 should be IB plus I2. But as the magnitude of IB is very less as compared to I2, so you can safely write I1 is nearly equal to I2. So we can say that the same current flows through R1 and R2. So if the same current flows through R1 and R2, it means that they are in series connection. Okay, as the same current is flowing through R1 and R2. So if we apply the voltage division rule here, the voltage across the resistor R2, which is written as V2 here, can be written as V2 is equal to VCC into R2 by R1 plus R2. This is the voltage drop across the resistor R2, which is calculated as per voltage division rule. Now all of these is based on the fact that IB is very small. As a result, I1 is nearly equal to I2. As both the currents are same, it means R1 and R2 are in series, so we can apply voltage division rule here. So by that analogy, V2 is equal to VCC into R2 by R1 plus R2, which is the voltage drop across resistor R2. Now, in order to find out the value of collector current and the collector emitter voltage, we have to apply KVL here. So first we will apply KVL in this loop, the lower mesh, to find out the value of IE, and then we will apply the formula that IE is nearly equal to IC, so we'll get the value of IC as well. So first we'll apply KVL in this lower loop, the base emitter loop. So here we will get, we can apply the KVL as V2 minus VBE minus IERE is equal to 0. Okay, V2 minus VBE minus IERE is equal to 0. Here I am using the second sign dominating method, point to point KVL. Okay, so please check out the videos which I have posted related to application of KVL in closed loops. I have posted 2 videos related to that in my channel, so please check out those 2 videos before you go with this. Okay, so the KVL equation here will be V2 minus VBE minus IERE is equal to 0. VB is the voltage drop across the base and emitter terminal. Okay, IERE is the voltage drop across the emitter resistance. Okay, now as I said, the KVL equation will be V2 minus VBE minus IERE is equal to 0. So IERE is equal to V2 minus VBE and IE is equal to V2 minus VBE by RA. Now as I said, we will apply the formula IE is nearly equal to IC. We know that the emitter current is almost the same as the collector current in a bipolar junction transistor. So by that we can write that the collective current is nearly equal to V2 minus VBE by RE. Okay, so we got the value of collector current, which is the output current for the common emitter BJT configuration. Now we have to find out the collector emitter voltage. In all of the DC analysis or DC biasing circuits, our objective is to find out the output current and the output voltage, because we plot the output characteristics using those 2 parameters. So in any BJT circuit related to DC biasing, your objective will always be to find out the output current and the output voltage. As the common emitter configuration is the popular configuration, the widely used BJT configuration, so all of the output characteristics is plotted using the collector emitter voltage, which is the output voltage, and the collector current, which is the output current. So we have determined the expression for collector current. Now we will determine the value of the collector emitter voltage. For that we will apply KVL in this output circuit. Okay, so how we can apply that KVL? See, from here, starting from here, we'll apply the KVL as VCC minus ICRC minus VCE minus IERE is equal to 0. Here we have applied the ground to ground KVL. Okay, here there is a ground. Okay, you can just imagine that it is not drawn normally because it is assumed that the students will understand, but here we will you have made that ground. So here there is a ground which is connected to the supply, and here there is this ground. So we apply ground to ground KVL from here to here, starting from VCC to this ground. So we got VCC minus ICRC minus VCE minus IERE is equal to 0. Okay, from that we will find out the value of collector emitter voltage. Okay, so here I have applied the ground to ground KVL. So we got VCC minus ICRC minus VCE minus IERE is equal to 0. So here we have again used IE is nearly equal to IC, that formula. So we got VCC minus ICRC minus VCE minus ICRE. Okay, we have replaced IE with IC here. Okay, so then we will take IC common and we get the output, the value of collector emitter voltage. So the collector emitter voltage value is equal to VCE is equal to VCC minus IC into RC plus RE. Okay, so when we applied KVL to the output side, the collector emitter side, we got this KVL equation: VCC minus ICRC minus VCE minus IERE. Here we are going to replace IE with IC, as IE is nearly equal to IC. So we get VCC minus ICRC minus VCE minus ICRE is equal to 0. We will take IC common with RC and RE, and we'll get the value of VCE, which is the collector to emitter voltage. So we'll get VCE is equal to VCC minus IC into RC plus RE. Okay, VC is equal to VCC minus IC into RC plus RE. That is the collector to emitter voltage. Okay, so here we have determined the value of the collector current, which is the output current, and the collector emitter voltage, which is the output voltage. Okay, so in any DC biasing circuit, this will be the objective of application of the DC analysis, to find out the output current and the output voltage, and then to plot the output characteristics, okay, at constant base current values. Okay, so then whether you use it to draw the load line or anything, that is the secondary purpose, but the main purpose is to determine the output current and the output voltage. So here we have determined the value of the collector current and the collector emitter voltage using KVL equations to the input and output load. So we have discussed the four methods of DC biasing, that is the base resistor biasing, the emitter stabilized biasing, the collector to base feedback biasing, and now the voltage divider biasing circuit. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical and electronics engineering. Have a great day. Thank you very much.